All right, this lesson is comes roughly from the last two sections of this chapter, or at least the last two that we're going to deal with. Um, and, the second one is called The Fundamental Theorem of Algebra, so you know it's something that's fairly important, right? So here we go. So remember that another term for the solutions to an equation is called the roots. And the roots of polynomial equations can be real or they can be imaginary. Okay, we know what that means. That means that they contain I, which is the square root of -1. Real roots can be rational or irrational. Irrational roots usually have a square root of some kind that can't be simplified. So both of these are the results of taking square roots, these imaginary roots and the irrational roots. And we know where that comes from, right? It's always in the quadratic formula, you've got plus or minus the square root of b squared minus 4ac. Or sometimes when you're solving by taking square roots, you might get x squared equals, and eventually, in order to get down to the x, you take the square root and you have to include plus or minus. So what that means is that irrational roots and imaginary roots always have to come in pairs. Because of the plus or minus, they have to come in pairs, meaning there is always an even number of these. So the conjugate root theorem, which comes from the first section, says that if you get one root which involves an I or a square root, then you must have the conjugate pair, right? The conjugate is a word right there. So, for example, this first one here is talking about irrational roots. So if you have 2 plus the square root of 3, you must have 2 minus the square root of 3, because where did it come from? It came from the quadratic formula, and there was a plus or minus. Same thing goes if you had imaginary roots. If you have 2 plus 3i, you must have 2 minus 3i, because where did it come from? Quadratic formula. So that'll help us to determine, especially when it comes to the imaginary roots, which we are asked to know the number of, how many are there? Imaginary roots are always an even number. It's never going to be 1, 3, or 5. It's always going to be 0, 2, or 4. So a quartic polynomial, we know what that means, x to the 4th, has rational coefficients. If the square root of 2 and 1 plus I are roots of this polynomial, then what are other two roots? Again, if you have one irrational, you must have the conjugate, and the conjugate is what you get if you just switch the sign. Just think of this top one as plus or minus. If you just have the square root of 2, again, maybe you can think of that must have happened by solving by taking square roots. If you get the plus square root of 2, you must have the minus square root of 2. Right? Try to do the same thing here. This one is a cubic polynomial. It has roots of 3 minus 2i and 5 halves. So what is one additional root? So hit pause. When you're done, hit play. So a cubic polynomial, because it's x to the 3rd, has 3 total roots, and 2 of them are given here. One of them is an imaginary number, which must have a conjugate pair of 3 plus 2i. Right? Now there's your 3 roots. The key point being that number is rational. And there's no theorem that says that there's any other rational roots other than 5/2. So don't try to take a rational number and do the same thing that we did with imaginary or irrational. Does not apply. Okay, the fundamental theorem of algebra comes from the second section that we're pulling from today, and restated in my text down below here, it's that every polynomial has exactly as many roots as the degree. And remember, the degree is the value of the highest exponent. And so these are all actually taken from a different section, but just to show how many complex roots would we expect. And in fact, I'm showing functions, so they would be zeros, but how many would we expect? And you can see if it's 7, if it's a cubic polynomial, you expect 3. If it's quadratic, 2. Is it a 6th power? 6. Whatever is the highest exponent, that's how many complex roots there are. Now, how many real are there? This theorem doesn't talk about how many real and how many imaginary. It just says that the total, the real plus the imaginary, which equals the complex roots, is equal to the degree. So if I circle the highest exponent in every one, that's how many. Now, I do know something about how many imaginary roots there has to be. Because what did we say about the imaginary roots? They always come in pairs. So if it's a cubic polynomial here and has a total of 3 complex roots, the number of imaginary is either 0 or 2. It has to be an even number, less than 3. Here's a quadratic. It has 2 complex roots, so the number of imaginary has to be 0 or 2. Right? 6th power. The number of imaginary roots must be 0, 2, 4, or 6. It has to be an even number, less than or equal to the degree. Now look at this one here. 9th degree, so there's 9 complex zeros or roots, and that means the number of possible imaginary roots would have to be 0, 2, 4, 6, or 8. The number of real roots has to be at least 1. There will always be 1. So I might have to make a change to this slide, but let's just see. The number of complex roots equals n. The possible number of imaginary roots are even numbers less than or equal to n. That's true. The possible number of real roots equals the complex roots minus the imaginary roots. And the thing is that we can find the number of real roots by looking at the graph. We just have to make sure that when you're doing that, that I count them accurately. For example, let's see, this one has how many turning points? 1, 2, 3, 4. So it's 4 turning points. So it's probably a quintic, 5th degree polynomial. It has x-intercepts, which we know are zeros. 1, 2, 3, and then this one is a double 0, so I have to count that as a double. So that's actually 1, 2, 3, 4, 5. There's 5 real roots or zeros of this fictional quintic polynomial. So how many imaginary are there? There's none, because there's a total of 5 and they're all real. I can see them all, right? But if I didn't count this one as a double, then I would have 1, 2, 3, 4, and that would mean there's 1 imaginary. Well, that can't be. Remember that the imaginary zeros have to come in pairs. You never could get just 1. So, what are all the roots? Well, this is what it was supposed to say. What are all the roots of this polynomial equation? So instead of answering that, this is what we're going to do. And the same will go for the homework. Get the number of complex roots, the actual real roots. Just take it from the graph. And from that, you ought to be able to figure out the number of imaginary roots, understanding that must be an even number. So let's bring out the Desmos. This is a quintic polynomial, right? So how many complex roots are there? There's 5. Okay. And let me zoom on this, zoom out. I mean, it's easy to see. Here's our real roots. Looks like there's one at -2, 1, and 2. That's 3. Okay. Now you might ask whether it's possible that this graph comes back around. You know, maybe after I get to 10, it comes back around. I could keep zooming out. There's never going to be a guarantee that it doesn't cross somewhere. But how many turning points do we expect from a 5th degree polynomial like this? And remember that the answer to that is 4 turning points. So, you know, clearly there's going to be a turning point at the top here. There's a turning point here. That's 2. But even this little wiggle in the graph right here, I mean, it's not really a relative max or min, but right there, that's probably the other 2 that brings up to the 4. So, I mean, I'm very confident that these are going to be the only 3 zeros. So let me do a little snip. Take a screenshot of that. Okay, and with that, here's our answer to our questions. The number of complex roots, 5, right? 5. The actual real roots, -2, 1, and 2. The number of imaginary roots. Okay, well, there's 3. There's got to be a total of 5, so there must be 2 imaginary. We're not saying what they are. We're not going to try to solve for them, although that could be done. We're not going to do that. We're just going to understand how many imaginary roots are there. I try to do the same thing on this. What do we need to do to this one before we can start graphing it? And the answer is we've got to get these terms to the other side, right? I'm going to put it over here. X to the 4th plus 2x to the 3rd minus 13x squared plus 10x equals 0. So go ahead and try to graph that and see if you could answer these 3 questions based on the equation and based on the graph. So hit pause. When you're done, hit play. So again, this is something we need to do in Desmos. So we have x to the 4th plus 2x to the 3rd minus 13x squared plus 10x. And no plus 4. So does that look right? That looks right. Here's our graph. It's a quartic polynomial. So we should expect that there's going to be 4 complex zeros. In fact, I see 4 x-intercepts. I say zeros. Zeros are roots. I see 4 x-intercepts, -5, 0, 1, and 2. So let me snip it. Okay, and answer our questions. So the number of complex roots is 4. The actual real roots from the graph are -5, 0, 1, and 2. The imaginary roots must be an even number. Well, there's 4 total complex, which means real or imaginary, 4 real zeros, which means there are no imaginary zeros, right? Because we can see they're all there. So I believe these 2 examples were asking us specifically about the roots because these were equations. And now it's actually asking us about zeros, but even I'm not going to fix this right now. But in the end, I think roots and zeros are essentially the same thing. So you could see, though, it's starting with an f of x equals. That's what makes these things zeros and not roots. So again, we're going to answer the same questions. Doesn't really change fundamentally what we're doing here, because the way we find the roots of an equation are we graph the function anyways. So let's go to our Desmos. And this is going to be x to the 4th plus x to the 3rd minus 7x squared minus 9x minus 18 and make sure I got all that in there correctly. And it does look good. So now I'm looking at this graph. I mean, I can clearly see that there's two zeros here, once and twice, but I'd kind of like to see what else is going on with this graph, because I kind of expected with a 4th degree polynomial that I could have 3 turning points. And let's see, there you go. So they were all a little bit low, but there they are, 1, 2, 3 turning points. And so again, here's our 2 zeros, -3 and 3. Okay, let's snippet that back to the slides. And I'm going to, just for completeness, show the turning points. Drag that away. Okay, and now we're going to answer our questions. How many complex roots? 4. Why? Because of that 4 right there. It's always the same. That should be the easy part. How many, what are the actual real roots from the graph? Looks like -3 and 3, which is a total of 2. So how many imaginary roots must there be? Right? There's a total of 4 real or imaginary. If 2 are real, 2 are imaginary. And last, again, find the zeros of this quartic polynomial, 4 terms, quartic polynomial by doing the same thing, right? Go to Desmos, hit pause, hit play when you're done. A bit of gymnastics here. Oops. So we have 2x to the 4th minus 3x to the 3rd minus x minus 6. Does that look good? Pretty much. Let me bring that up. Let me hit the house to make it go back to the normal resolution. And maybe I'll scoot it up just so I can see what's going on. So notice this is a quartic polynomial, which means we should expect 3 turning points. And again, there is a distinction between what's a turning point and what's just kind of a wiggle in the graph. And there's clearly one absolute minimum of this graph right here. But these 2 here, also this little wiggle, you can kind of think of that like a maximum and a little bit like that like a minimum, which means that there's no other wiggles going on anywhere on this graph. We know we've got all the important features of the graph right in front of us. Okay, so click and click. And snip. And then answer the questions. How many complex zeros? Well, it's a quartic polynomial, so there's 4. What are the actual real zeros? Oh, looks like I lost that one when oh no, it's right there. -1 and 2. What are the imaginary? What's the number of imaginary? Well, if there's 2 real and there's a total of 4, there must be 2 complex. Okay, so that is not just the end of this lesson, but the end of this unit. And you know, I'm pretty happy with the way this last lesson ended and what we've done totally with this chapter, which is 75%, if not more, things that you can do with Desmos, and not in a cheating way, not in a way of going around the standards, but in a way of understanding polynomials. So that is the end of that. And let me just fix this a little bit. We're going to find the number of complex, the actual real, and the number of imaginary. And let me stretch that out like that. And let me hit pause. And one last thing. We're not doing those. So just these problems. Again, these are just naming the conjugate root or 0. And this is doing what we just did on those last 4 slides or so. Just find the number of complex, find the actual real zeros or roots, and then find the number of imaginary. Finito.